In this lesson, we're going to discuss the deflection of beams. So, a beam. A loaded beam will sag and deflect, as shown in figure 15.1. The beam design may be adequate for bending moment and shear, yet may be unsatisfactory for deflection. Excess deflection can cause crackings of ceilings, walls, floors, and other problems. Other serious issues due to a lack of rigidity. Your system could have changing in floor and wall alignment, improper functioning of roof drainage systems, undesirable vibrations from various live loads. Lack of rigidity in a floor system may lead to vibrations caused by pedestrian traffic, for example, and misalignment of precision equipment housed in a building. These are mostly structural issues. So here's that figure 15.1 showing the beam deflection. Okay, so you'll have like this elastic curve deflection from the beam based on these two loads. Okay, that brings us to our first definition, elastic curve. That's the curve position the neutral axis assumes when the beam is being deflected. Okay, so let's look at this derivation of radius of curvature. Okay, so here is an example of a beam being bended, a segment of a beam being bended. We're defining this radius of curvature. The elastic curve is this new curve of where the neutral axis is, but the radius of curvature is from this origin point down to that elastic curve. There's a derivation in your textbook. It talks about really small deformations, but it leads to equation 15.1, which was radius of curvature equations. So what this is the tensile or compressive bending stress at the outer fiber, F sub B, equals E, which is the modulus of elasticity, times C, which is the distance from the neutral axis to the outer fibers, all divided by R, which is the radius of curvature of the elastic curve. We can take that equation and rearrange it to solve for R, and what we have is EI over M. Okay, so what this says is that the radius of curvature is a function of the moment at that point. Now again, this applies at a point on the beam. So there's our first two equations for this chapter. Okay, equation 15.2 shows the radius of curvature at any point is just related to the moment, and then EI is essentially the stiffness of the beam. If the moment is 0 at any given point, that R becomes infinite and the radius is essentially a straight line. And the term EI can be thought of as the beam stiffness. Okay, so in this figure what we're looking at is two beams with the same loads, P and P. And we have an unloaded position of the beam here, and then we have this loaded elastic curve position. Okay, so what this is showing us is that if the beam has a larger EI, or stiffness, then our deflections are smaller, hence this Y deflection. Y is the maximum deflection. So in this case, Y is smaller because EI is larger. In this case over here, EI is smaller, so therefore your deflection is larger. So a beam with smaller EI deflects more. E times I, which is your modulus of elasticity times your moment of inertia, is a indicator of the stiffness of your beam. So when we come to calculating deflections on beams, we really, essentially it's a calculus thing, in that if we were to integrate the moment diagram, we would come up with the deflections, but we're not going to do that in this course. What we're going to do is we're going to apply two basic methods, the first one being the formula method that uses beam formulas in Appendix H, because those formulas were worked out for us and we could take advantage of them. The other one is the moment area method, which is in some cases a little bit cumbersome, but we'll talk about that in a minute. But for all of these deflections, we need to assume something about our system. Okay, first of all, the maximum bending stress does not exceed the proportional limit. And second of all, the beam is homogeneous. It obeys Hooke's law. It has equal modulus of elasticity and tension and compression. A plane section through the beam before bending remains a plane after the bending takes place. The beam has a vertical plane of symmetry, and the loads and reactions act in this plane perpendicular to the longitudinal axis of the beam. That's your parallel force system. Deflections are relatively small, and the length of the elastic curve is the same as the length of its horizontal projection. Small deflections. And then deflection due to shear is negligible. Shear deflections are generally much smaller than deflections due to bending moments. Okay, so if we were to talk about the formula method, Appendix H provides beam formulas. It gives the beam deflection at any point along the length of the beam. It gives the maximum deflection. It gives the location of the maximum deflection. Here is an example. So this is the first example. There's like 14 different beams that are covered in section in Appendix H. Here we have what the reactions are. It tells us what the reactions are. It tells us what the shear load is at any point along that. It tells us what the maximum moment is. It tells us what the moment is at any point. So this formula tells us what the moment is at any point. That's this x here. Okay. It tells us what the maximum deflection is at the center, and it tells us what the deflection is at any distance x from the left end. So this is how you use these tables. You have a bunch of formulas that tell you what it is. You have a picture that describes what this moment diagram looks like. Now, when we start doing the moment area method, these tables will be good to look at because it tells you what the shape of the moment diagram is. I'm going to stop this video right here and pick it up with the next one.